Can you hear me? Hello, Horse? Hello?
Yes, sir.
Yeah, I forgot to send the notice. Today's class? Is it? Then ask other students to join. Hello? Could you see my screen? Hello?
Yes, sir.
Yes, sir.
Okay. Well, I want to talk about Tietze's extension theorem. This is definitely one of the most important results in mathematics, not only in topology and analysis. But before that, I would like to talk about what extension means. Okay. Now suppose you have a function when you take from R to R. Okay. And if this is continuous, then if you take any subset of this, non-empty subset, then if you restrict this function to Y, still it will remain continuous. Okay, but what about the other direction? Suppose I have a continuous functions here. No. Suppose I have continuous here. Is it possible? Now look. Is it possible to have? I have this only, and I want to see whether I can have a function like this. Is it possible to have H R to R continuous function such that when H restrict to Y, that is F. You are going the other direction. Okay, that is Hx equal to Fx for all x in Y. Okay, for all x in Y. Now look, I have taken continuous here, so I am going for continuous here. This is called an extension. This is a continuous extension rather. Look, any extension doesn't matter. You can, if you don't insist on continuity here, then you could take anything outside Y. But the question is the continuity, continuous extension. H is called, there may be more than one extension, is called a continuous extension of F to whole of R to R. Look, this is not always possible. Let me give you an example that if you take F01, 0 you can see that 1 you can keep if you want. Then, sorry. This is a continuous function. Okay. Like, so actually it's equal y equal to 1 by x. So as at 1, from 1 up to 0, 1. Okay, at 1, this is 1. Okay, basically it goes like this, asymptotic. Question is that, look, 1, you can take closer, doesn't matter. But on the right side, I can simply do that or anything like this. That I can extend. This will be continuous extension. Okay, line. You could take any continuous line, the graph, like this also you could take. But only this point, at the point 0, forget about the whole R. Forget about whole R. You won't be able to extend to 0 even. Okay, you won't have a function even like this. Continuous function. I can take h equal to something here at that, but continuous, such that hx is equal to fx for all x belongs to this. Particularly this thing I won't have it. I won't be able to define, I can define h0, but I want to be define a continuous h such that h0 equal to be f0. So say 0 is not defined, that's why it will be defined. For all x belongs to, sorry, here I had this. Continuous extension. So that problem is that 0 here. You can say the problem is that it was not closed already. That is the thing. So, but if you have closed it, look, like here, if I take I can take intervals, just not necessarily 0, 1. If I take closed interval, sorry, A, B, suppose you have, look here, suppose this is your A, this is B. If you have a continuous function, you have graph like this. Okay. Now look how usually how will you think of extension? I can take this. That means I can take fx equal to that's extending h basically. I will take h x equal to fv for all x greater than equal to b, and hx equal to, I can take other things also, fa for all x less than equal to a. That is this. So this will be a continuous extension to whole R. So that will, but it was closed. That is the thing. So the thing is that extension problem you are having, that you want to extend to a bigger set. Like look here, this extension depends on what quality you have here. Suppose you are doing linear algebra. Suppose you are doing linear algebra. You have two vector spaces. Suppose V1, you have a linear map. V to W. These are VW or vector spaces. Doesn't matter, you can take over R if you feel comfortable. Vector spaces. Now not over R. So UT, now if you have this thing, V1 is a linear subspace. Linear subspace. Linear subspace. Then if you restrict to this will be also linear. But what about other way? Okay. Other way means suppose Suppose you have other way. Here you have linear. Can we have that? You can call it S. It's linear. Look, linear, so I'm taking linear. When you do linear algebra, such that S restricted to V1 is T. That is, we have done linear algebra last semester. That is, SV equal to TV for all V belongs to V1. Okay, right? Look, if you have linear algebra, you did finite dimensional. If it is V as finite dimension, then it's not a problem because then V1 will be finite dimension. Okay, and you know that. So let me tell you that in general, any linear map actually has to be will be determined uniquely by its image on the basis element. So that suppose V is finite dimensional. Okay. Suppose V1 is a subspace, V is finite dimensional. Dimension of V, this is notation, it means finite. And suppose V1, you have this. How will you do that actually? Linear map. What you can do that, first to choose a basis element of this. This is finite dimensional, this is also finite dimensional. Suppose x1, xk is the basis of V1. Extend this to basis, extend it to a basis any basis can be extended to the basis of the whole thing, xn of V. Then you define for this, and then you do it defined linearly. That will be same thing. So first define Txj equal to whatever you want in W. Okay, you call it Wj. You pick up. It doesn't matter what you pick up. Where k plus 1 j n. And you leave them same, whatever is there. And then you extend linearly what thing, because any basis element, any element of V can be written as a linear, unique linear combination of this. So you take linear combination. So this will be done if it is finite dimensional. But what about infinite dimension? Look, argument is that if whatever basis you have, that you can always extend to a basis of V. Okay, because any linear independent set is contained in a basis element. So this will be always possible. That means what I'm saying, you don't need this. Suppose what I want to do that, you'll have to don't try it this way. Now look, what will you do? That suppose you have V1. Not necessarily I need any, you have this linear. Take P prime, that will be a basis of V1. Need not be finite. This is always true because this will be linearly independent, so it will be contained in a basis of V. Extend it to a basis B of V. It's fine. Hello, horse. Are you listening to me?
Yes, sir.
Hello. Extend it to a basis B of V. Then define on V. Then first you define T on whatever you call S. Define S on P. Like this. S V equal to TV if V belongs to P prime and as V equal to, you have the, you can define anything, choice. If V belongs to B but not B prime, your choice means choice from W. I have defined on basis element, then extend it linearly. That's the way we define linear map. So this is possible. Here the problem is not that. But point is that I can make your life little difficult. So what? Suppose I'm doing even finite dimensional. Suppose I have a map T. Call it Rn equal to V, suppose. Okay. And you take a copy of that. W V1 equal to Rn. Copy it. Basically copy M less than N. Okay. Basically, if you have this N tuple, then here you have this. Take this. This will be a subspace of this. This is up to N. Okay. So suppose I have this, a map. I mean, I can take Rn or another space. It doesn't matter. Suppose this is linear. Take Rn because you have the metric in that. You can take any, not necessarily any this N. You can take another N, P. Linear and continuous. I can talk about continuous. Here you have the metric, you have the metric, usual metric. Okay. Is it possible to extend to this with this property? That means, does there exist linear as well as continuous? Okay. Such that S restricted to SA as V equal to TV for all V belongs to RM, sorry. Because RM is a subset. RM means this thing I am taking. Okay. Yes. So here it's a problem. At the same time you want continuity. So depends on where to have the map in the beginning. That by extension means for a bigger space I will have the similar property. Similar property. Okay. So this is the next semester we'll do function analysis. This is the special case what I'm considering. The Hanmanach theorem. Hanmanach theorem actually some extension theorems. Hanmanach. Both were the big doyens of analysis, particularly Banach. What you can say, the probably one of the most prominent founders of function analysis. Hanmanach theorem. In fact, they are extension theorems. In fact, there is a theorems because Hanmanach theorem comes with a lot of corollaries. And in fact, in application, we apply corollary. So any corollary we just say by Hanmanach theorem. That is understood. You are applying one of the corollaries Hanmanach theorem. Original Hanmanach theorem we do not apply. We usually apply the corollaries. So that's why called Hanmanach theorems. These are actually extension theorems. Okay. So it depends. Like if you start with a group, like let me tell you that. Even in algebra, if you do it. Suppose you have in algebra you have a ring, and that ring is contained in S. And suppose you have with another ring R1, you have a ring homomorphism. Question is that whether I will have an extension like this. Extension here, the extension will mean since I am taking ring homomorphism, that will be ring homomorphism. Okay. Such that F, you call it phi, that means phi restricted to R will be F. It depends on what you are starting with, you will have. That is called the extension theorems. And that is basically useful in mathematics, in almost any branch. Okay. So Tietze's extension theorem, like I told you that if you have closed, you will get it. Tietze's extension theorem says that you don't need to bother about the proof of the Tietze's extension theorem. I won't give you the proof of Tietze's extension theorem, but you should be able to apply Tietze's extension theorem. Okay. Now Tietze's extension theorem apparently even they have given two forms, but let me explain that. Both the forms you should know. Suppose it is required that X is a normal space. This is Tietze's extension theorem. Okay. But again, for normal space, you remember the definition first. That if you have X tau is called normal. So I'm recalling the definition is normal. It's called normal if I'm saying look C, T are closed disjoint sets. You can take non-empty. Empty set you don't need to do it. Are closed disjoint sets. In X, then there exist open sets. That means they can be separated by open sets. Open sets U and V in X, that means X tau, such that C is contained in U, D is contained in V, U intersection V is empty. That is the definition of normal. Okay, right? And I told you the normal plus T1 is called T4. But some people by normal they take T4. And also I told you normal plus T1 is same as normal plus T2. That's why some people call it specifically normal Hausdorff space. Okay, for to say it is a T4 space. Okay, right. So that Eurytion's lemma, don't forget about it. I told you there are two types of separation. Separation by open sets, separation by continuous functions. Okay. Here the Eurytion's lemma says in case of normal we can do it separation by continuous function. Separation by continuous function is usually stronger than separation by open sets. So that means X tau is normal. You don't need T1 here. If and only if given disjoint closed sets. C and D in X. There exists F X to 0, 1. I told you you could take AB continuous function such that Fc equal to 0 and Ft equal to 1. Okay. So actually this Eurytion's lemma, why it's called itself is a big result. But people call it lemma because lemma is usually used to prove another result. Because this is used to prove Tietze's extension theorem. That's why people call it lemma. But it is unfortunate. It should not be called a lemma. It's itself a big theorem. Okay. Now the Tietze's extension theorem has two forms. One way it is simple that you look at if and only, but Which side is important, that I will tell you. Here's the extension theorem. First, you see that suppose X tau is a normal space. This is important. Without normal theorem, extension theorem, we can show that it won't be valid. X tau is normal, and suppose Y, of course, empty set, I don't need to do it, is a non-empty closed subset of X. Okay. Look, usually extension, how we write. Suppose you have a first version I'm giving. Y to R with usual topology. And Y you have actually subspace topology, tau Y. You should understand. Suppose this is continuous. Non-empty closed, this is very important. Closed. Then there is an extension X tau. Look, this is standard thing. People call it F hat. You can look. There exists when you take broken arrow, this means that it was not there before. You have created, and when we do the straight arrow, that means it was there. So there exists this continuous such that F hat restricted to Y is F. That is F hat Y equal to Fy for all Y belongs to Y. Look, this is important, continuous. Here I have continuous, I have continuous. Okay, so this is one version. Actually, it said if and only if I have. The other way you can prove, that is, proof is simpler. You don't need Eurasian's lemma. That I have given you one problem there. You should look. Okay, I should give you the assignment also. You should ask so this is one version, that extension. But suppose it is real valued, but it is a bounded function. That means to have this now. So should I am not erasing it. But another version you can have. Suppose you have Willard has proved this, and they said from the proof it follows. That means suppose I have the bounded function. That means its range is inside this closed bounded interval. Then I will have this extension with the same property. F hat. That means what will be the range here? Same range will be valid. So if you have unbounded function, it will be continuous unbounded function. If you have a continuous bounded function, it can be extended to a bounded continuous functions. That's the idea. Okay, even boundedness will be preserved. Okay, like this. So if you have this, you can have this. And both ways the converse is also true, that if you have this, then extra will step in normal. But that is easier to prove. But this is Tietze's extension theorem, two versions. Usually people prove it, then you give it as a corollary. But Willard also has a sort of given corollary, I think. But he said from the proof of this, it is clear that because the way we choose, that it will come that. Okay. So first thing, Tietze's extension theorem statement is very simple. That you'll have to understand. That is very important. This is twofold. If the range is this, it will be similar. If the range is this, now let me give an explanation that how we'll do that. Look, I will teach you again connectedness. I'm just telling you that suppose we have last semester you have done this, the connected subset of R. These are actually intervals. Connected subsets are intervals. Okay. Now suppose what will happen? Suppose we have a connected metric space. Look, metric space is normal. Okay, I'm giving you the simple example on that. Okay, and suppose it has more than one point. Okay, fine. You can generalize many things on that, but I'm saying suppose this is XD connected metric space. I'm saying this space has to be very huge. Its cardinality has to be greater than equal to C. Okay, if you had got more than one point, okay, it not only will be infinite, it will be hugely infinite. How will you do that? Okay, fine. Look, so it has got more than one point, so you choose 2 points. Okay, so there exists a continuous function that you can take D function. So there exist a continuous functions. First, right now, I'm not doing thing the other extension. I'm just giving you this the technique of the proof. So there exists a continuous function. Xt to R such that fx equal to 0, fy equal to 1. Okay, fine, got it. Now, right now again I'm telling you, I am not doing it right now. I can give a, I am thinking of giving a problem in the exam. That's, but you will have to use basically similar arguments in that. Now look, x is connected, so fx is an interval. X is connected, continuous image of a connected space is connected. So fx is an interval in R. But what is the definition of interval? That 0 and 1 is here. Okay. So that means entire interval this will be subset of this. Right? But this has got C cardinality. So its cardinality has to be greater than equal to C. But remember that problem I use, I have given a note. The cardinality of X, well, is greater than equal to cardinality of Fx. It can only decrease, not increase. But cardinality of Fx is this. Okay, right. Got it. Well, how THA comes in this account? Here it doesn't come. But I can tell you that if I go through subspace, this function is very important. This function is very important. Okay, so that, well, look how much I have used metric space. I have not, you may wonder that I have not, because I am just wondering whether I should say is link it to THA so that I will lose the problem for the final, for your minor exam. So, but look, suppose now I do that connected Tychonoff space. Still, you can have that result. You have continuous image of a connected topological space will be also connected. Connected Tychonoff space. Can you think of that? Suppose it has more than one point. Same argument will give you because you needed a function. You didn't need metric space. And all you need continuous image of a connected space is connected and connected subsets in R is intervals. I will talk about all these things when connectedness comes. More than one point. Okay, right? So you can prove that the cardinality of x, same argument, has to be this. Because Tychonoff space, remember, completely regular. So you take 2 points, they are closed. So by complete regularity, I will have a function, non-trivial continuous function, and then the same argument will be valid. Okay, right? So let me then. I will talk about again this but I want to talk about the exam first. You take, let's take forget. Aliprantis Barkinsaw. I'm giving the problems assigned. Let me tell you that. This is page 86, 87, and problem you will do it number 1 to 7, 9, 11. I have just omitted 8 and 10 right now, but right now I'm giving you this many 9 problems. Okay, right? Is they're talking about locally compact topological spaces. Locally compact I have not talked about, so that's why I will talk later on that. And that exactly what I was doing. He's taking 10 connected normal space. This means T4 space, but you could do it for Tychonoff. That what I was giving the argument actually. Either singleton or uncountable. This they are doing it. Okay. Since I have not taught about this semester, I'm here to teach connectedness. That's why I'm not assigned. But you can do that, like the same argument I have given. First thing you should make sure that you do that problems. Okay, right? Well, yeah, let me tell you that. If you are reading from Aliprantis Barkinsaw, it is their theorem 10.5, page 81. Okay. So here, actually, equivalence of 1 and 3. That's the classical equivalence of 1 and 3 can be separated by a continuous function. That is actually Eurytion's lemma. They have added 2 more conditions and they said Eurytion's lemma. They have actually added one Tietze's extension theorem. This is Eurytion's lemma. What I say that this is normal if and only if two disjoint closed sets can be separated by a continuous function. That means what I emphasize in case of a normal space, separation by open set, separation by continuous function, there is no difference. Okay, so 1 and 3. And here in 4, 10 I'm writing. It is actually Tietze's extension theorem, 4 and 1. Equivalent, they're saying. Of course, I told equivalent. I just put in one, I talked about one direction. This is Tietze's extension theorem. Okay, well, for the range 0, 1, that is same as AB. Okay, and but they are saying Tietze's extension theorem. We can have a look at the proof. This proof is really big. They are saying Tietze's extension theorem 10.6. They are calling Tietze's extension theorem. Here they are taking range is R, but actually these two together, as I explained, that is Tietze's extension theorem. That means, again I'm telling you, if you have a normal space, one direction I'm taking, other direction, and let me tell you that F, Y, Y is closed. X tau normal. Y is closed in X. If you have this continuity, then you can extend a fact. This is also continuous. But instead of R, if you have this, that is also true. Then range will be inside this. There is two forms of the extension theorem. You'll have to, well, that I think you will do the problems, then I will again talk about this. I'm coming to that. Okay. But here, they're talking about if and only if. So that I want to tell you that how the other side is easier actually. That means here you have the extension, you'll have to show that this is normal. In order to prove this, okay, let me tell you that what you need to prove. That I have given an exercise. I think I state the result in my notes. I said proof exercise. What is the proof? Suppose X tau is a topological space. Okay. And suppose X equal to A union B. A, B are closed. This is called Pesting lemma. Such that you have a function. Look, you have a function from A tau A to R. Suppose you have such that it is continuous. Okay. Similarly, you have another function G P tau B in the subspace topology continuous. But now suppose A union B, so that A intersection may not be empty. But if I say, now look about this function. Suppose assume you are assuming fx equal to gx for all x belongs to this. That means where they are overlapping, these two functions are equal. Then if you define this function, new function, the whole thing. Define hx equal to fx if x belongs to A. Define gx if x belongs to B. Look, this is well defined because of this. This you need. Otherwise, it won't be a function. If this is not satisfied, it has to be. So I am giving you this. Then H is continuous. H is continuous. This is called the pesting lemma actually. Instead of closed sets, if you took open sets, still the same argument will be valid actually. Also, you can take any finitely many closed sets, finitely many open sets. Only thing in their intersection, they should have the same value, the functions. Like f1, f2, f3, and that. Okay. Look, basically how will you prove? Suppose this C is a closed set. C is closed. Since you are taking closed, you take that criteria. Inverse image of any closed set is closed. Then it is continuous. C is closed in X tau. Now look, F inverse C. It is in X. Okay. I have taken H actually. Okay. You can take H. H inverse C. It is coming into X. Okay. So that this is basically X. So this is Okay, but here H is same as F. So this is F inverse C intersection A. On A. And this is G. Well, what will you do now? Look, F inverse C. I want to prove this is closed. They are closed sets. The subset of A is closed if and only if it is closed in X. If it is closed in X. So this is actually, I have taken F. So this will be F inverse C. And this is union G inverse C. Now look, this is closed in A, but A is closed. So this is closed in X. Similarly, this is closed in X. So union of two closed sets is closed. So it will be closed. This is called pesting lemma. So by using this pesting lemma, you can prove the converse direction. That they are saying that if and only. But that means the value of the thesis extension theorem in the straight direction. That you have the extension if this is normal. Okay. So that first thing I'm putting in the exercise. So thesis extension theorem again. Let me tell you that what I'm saying. X tau should not forget normal. Okay, X tau is normal. C is a closed set, or Y you could take, sorry, take Y. Closed set E X. So here you have this thing. I'm writing the both diagram. Y, tau Y. Suppose you have a function, continuous. Then there is an extension. This means you're proving there exists broken line, a fact, continuous. That means a fact restricted to Y is F. That is a fact Y equal to Fy for all Y belongs to Y. And this diagram also valid. If you have this, that is bounded function. Here need not be bounded. If you have a bounded function, this is continuous. Then with the same range, a fact and a fact restricted to Y is F. What I am emphasizing, insisting that range you can have, that you can afford to have, range will be the same in that. Same means range will be inside that. Okay. I'm not saying range obviously may not be the same, but the range will be inside that included. If it is R, it will be real valued. If it is bounded, it will be bounded. That's the thing. So this is called the Tietze's extension theorem. Okay, so let me see that. What else I can prove that? Okay. Well, let me come back to that African metric space of that xt. Okay. So xt, you have, it is normal that I proved. What function we gave? I think that here in Halipranthis Bakilsa, make sure that this is very important. Problem number 2, page 86. Okay. Now xd normal, usually how we prove it. Okay. That. because actually we get separation by continuous function. And what separation? Suppose A, B, two closed sets, disjoint. Of course, I am assuming non-empty. Then you take this function fx equal to dxa. That is exactly problem number 2. This is very important. You should do it. Look, whatever result you are trying to prove, first you see that whether you can prove it for metric space. If you can't prove it for metric space, forget about it. You won't be able to prove it for topological space. So the first thing you should see, and then you see that what arguments you are using for metric space, whether they are valid for topological spaces or you are specifically using some metric. Okay, so this function tells you something more. What is more? It tells you, look, it tells you that fx equal to 0 if and only if x belongs to A. Because if x is 0, then this has to be 0. Then x belongs to, if and only if x belongs to A bar. That is, and fx equal to 1. This has to be 0. If and only if, sorry. If and only if x belongs to P. समझ गया? That means you are getting A equal to F inverse 0 and B equal to F inverse 1. Look, when you separation by continuous functions, you are having basically you have this subset, but here you have exactly equal. So this is stronger than that. For a normal space, you don't need that separation by continuous functions. So this, they are talking about problem number 7, G delta set and this for a closed subset of a normal topological space. So 7. Look, problem. Okay, right? Well, now again they're defining perfectly normal. Okay. Look, if you have this stronger condition, then obviously it will be normal, but it's stronger. So this is called perfectly normal. So perfectly normal. I am taking basically some tutorial also. कहाँ चला गया रे? Page 86 बताया. Problem number 9. Perfectly normal. This is stronger than normal. Okay, but it is very useful if you have it. Okay, because you're dealing directly with the functions of that. Okay, so make sure this you do this one. Okay, and they're talking about G delta set, G F sigma set. So I am recalling that. What is G delta set and F sigma set? G delta set means this is like this intersection, countable intersection of open sets. This need not be open. In R you get this thing. Okay, like any point here X. Each of them is open in R, but this is not open. समझ गया? So this is called, if you have countable intersection open set, it is called G delta. X sigma is you have this. Fn, each Fn is closed. That is countable union of closed sets. Take its inverse. Sorry, its complement. So what will you get that? That will be countable union of that. Closed sets. What will you get that? Another union. Here it should be another. These are closed sets. Countable. This is closed sets. Countable. Countable union are closed sets. Okay, but this is open. This is not closed. So G delta set, F sigma set. But why is that? There is another problem there. What is that problem? Okay, problem is I have not given actually what the some application of theory extension theory. I am talking many things because let's not forget of them. Okay, so that the metric space is the problem. So that every open set is a metric space. Every open set is an F sigma set. And every, so it's up, you take complement, you will get that every closed set is a G delta set. These are very important. You should be able to prove it. Okay. How to prove it? Look, if you have a continuous function, f inverse 0. Okay. This you can get as this. The other side. 0 is this. If you have continuous function, each of them is open. Okay, so it will be a G delta set. And if it is closed, so it will be, it is closed if you continuous function. So such a set will be G delta. Okay, anyway, it is called in topology, there is, it's called a zero set. Every zero set is a G delta set. What I am talking about in a metric space, every closed set is a G delta set. That thing, let me tell you that. Here, yeah, problem number 7, I have already talked about. Problem number 7, that you should do. Page 87. Okay, right. Okay, lest I forget, I should tell one thing. Your exam is going to start week after that, not the next week. So you tell me which date and which time you want to take your exam for minor exam. So suggest me date and time. And syllabus will be whatever I teach until the next week. Okay, so you should tell me that. And again, like the previous semester, it will be 40 marks. There will be probably 6-7 questions. But let me tell you something. Don't try to help your classmate at that. Okay, because I won't give you enough time. I will give you probably 1.5 for everything, including sending me this. So it's not, you'll have enough time to help your students at that. And of course, it will be open notebook, open book, open notes, everything. But again, I'm telling you that if you all the time, if you keep opening your book and notes, you are not going to do well. In the US, they have that concept long time back, open book exam, open notebook exam. I studied there. But the thumb rule is that if you open your note, open your book more than 5 times, you are not going to do well in the exam. Okay. Right? It is basically if you have some doubt about some statement of the result theorem and that, you just see that what is exactly the precise statement. Okay, like the extension theorem I'm telling you, but you should not have the doubt. Okay, so make sure that you spend time on your own work. Don't try to help your friend. That will boomerang you on you. That way you will do worse. Okay, right? So that make sure that, and you should suggest to me. Now I am going to finish it. I will do it tomorrow and that. But let me tell you something about theories and extension theorem. I want to talk about it. That okay. Hmm. Actually, I talked about a lot of things on that. Oh, this problem almost I talked about everything in that. So again, I'm telling you that here's the extension theorem. I am telling you. Again, let me tell you that. Just understand the statements. You don't need to bother about the proof. Both version. Okay. Continuous and bounded continuous function. Continuous and bounded continuous function. Similarly, Eurytion's lemma. You don't need to bother about the proof. If you are interested, you can look at the proof. You can tell me. Okay. Eurytion's lemma. Okay. Right. Just mentioning that last semester I taught you what is the extension theorem. I'm telling you that. Okay. So Eurytion's lemma. That you do. Okay. Now you should do it. Another extension theorem I'm talking about that. Suppose that I think I did last semester. Probably I suggested some proof. Can you think of that? Suppose xt, it is an Alipranthis Barkinson, is a result. Let me tell you that. xt y rho, you have a uniformly continuous function. Because in a metric space, we can talk about uniformly continuous function. And suppose this is complete. Well, then this you have the completion. Again, we did the same thing. This is called the completion. Then you have extension of this, not only the uniformly continuous function extension. Look, x is dense in actually this. Then you have this uniformly continuous function. So let me tell you that what result I'm talking about. Okay. Yes. It is the giant thing you have it. But actually for completion is unique up to isometry, you need that theorem. 6 point Naliprantis. 6.19, page 45. Make sure when you are talking about the theory extension theorem, read that and you read the with proof. Read with the proof. Okay, here actually they have not taken this thing completion. They have what they have taken that. Suppose, but let me tell you that the version they have given. XD is a metric space and A is closed in X Then what are they saying? Suppose, sorry, you have then it can be extended to a bar closure. So that was a special case. So in Yang, but it can only extend to up to its closure, not beyond that. Not beyond that. Okay, this is also an extension theorem. Okay, beyond that. So make sure that you read the proof. Okay. You should discover some good technique. You should discover. Read the proof. That's the next exercise. I think you should be able to understand the proof. If you don't understand, ask Gaurav. You can ask me also. Okay. So this is thing. But well, after this you have uniformly continuous function. That is. But can you look here? About Tietze's extension theorem I was talking about. Now suppose here I have a metric space xt, special case. Suppose you have A is closed in X. Suppose I have that I'm leaving the question to you. Think about it. You can search the literature on that. But look what I'm saying. Suppose AD is a bounded function. That means you have this. You have F. Since these are metric spaces, I am not only giving you continuity, I am giving you uniform continuity. That's the question. Uniform continuity. By Tietze's extension theorem, you know it can be extended to the whole as a continuous function. I'm taking bounded. For unbounded, you can think of that. Okay. Unbounded, it need not be true, what I'm going to say. But I have taken uniformly continuous. Can I have uniform continuity here? That is the question. By Tietze's extension theorem, it can be extended to a continuous function. I don't need uniform. But since I am giving you uniformity, I'm dealing with everything about metric space. Can I have that uniform continuity? That's the question I'm leaving it to you. If you find in the literature some extension theorem, it will be good. Try to find out that whether it is possible. Is it possible? If yes, who proved it first? Who gave it? Okay, so right, well, so this much again I'm telling you should look at Tietze's extension theorem very well. Okay, right, what else I'm thinking? I want to teach you something so that you don't say that in the exam I have not done this, I have not done that. Okay, right, so that theorem 6.19 you should do it. Okay. I think I will leave it to that, but make sure I have not given you actual some application of that. That I only give for connectedness and that is not even extension that. Okay, but that is a different cardinality. But it's an extension theorem. Okay, right? Just think about that. There's actions. I will teach you tomorrow. Tomorrow I'll take the class. Okay, not tomorrow. It is Friday, so Monday. Monday is which date? That I will 7th. I will take. So I am just giving you time in the weekend. Make sure to do the TH extension theorem. And also try those problems from Ali Prantis Barkins of page 86, 87 I have given. Okay, so think about it so that be prepared. Next week, you ask whether Saurav can have 2 tutorials on that and suggest me date. Talk to your classmates. Okay, see you on Monday. Okay, bye. कोई फिल्म में की है